Verifying a trigonometric identity. Recall that an identity is an equation which is always true. When you were first learning to solve linear equations, one of the things that you learned was to recognize that if you had something like 3 times x plus 2 equals 3x plus 6, that's two ways of writing the same thing. This equation is true, which means that all values of x are solutions. A trigonometric identity works the same way, except instead of just having these nice simple equations, we're going to be talking about equations that have trigonometric functions in them. You're already familiar with several trigonometric identities. The reciprocal identities tell us that the secant of theta is 1 over the cosine of theta, that the cosecant of theta is 1 over the sine of theta, and the cotangent of theta is 1 over the tangent of theta. Those are important in working through performing the operations of secant, cosecant, and cotangent on a calculator, because most calculators don't have those functions built in. You're also already familiar with the ratio identities. Sometimes called the quotient identities. Tangent is sine divided by cosine. We know that that's true, or we can verify that that's true, by remembering that the tangent of theta is the opposite side of the triangle divided by the adjacent side of the triangle. Sine is opposite divided by hypotenuse, and cosine is adjacent divided by hypotenuse. If we take the fraction on the right and simply multiply top and bottom of the big fraction by the hypotenuse, then we end up with equality. So tangent of theta is equal to sine over cosine. And then because cotangent is the reciprocal of tangent, cotangent of theta is the reciprocal of sine over cosine, namely cosine over sine. The ratio identities and the reciprocal identities are going to be very powerful tools for us in trying to work through the properties of these equations and work through identifying whether the other equations we look at are also identities. Up next, a property that you saw recently when you were looking at the graphs of sine and cosine is that sine of theta is an odd function. That is to say, because of the shape of the graph of sine, which looks something like that, if you take sine of the opposite of theta, you get the same thing you would get if you took the opposite of the sine of theta. Cosine of theta is an even function. Remember, the graph of cosine is symmetric about the y-axis. So the cosine of the opposite of theta is the same thing as the cosine of theta. It doesn't really cause any issues whatsoever. The last set of identities that we'll talk about for now are the Pythagorean identities. The Pythagorean identities come out of the Pythagorean theorem, as the name suggests. So if I have a right triangle, I have some angle marked. The Pythagorean theorem tells us that the legs opposite squared plus the other leg, which I called adjacent squared, is equal to the hypotenuse squared. If I choose to divide both sides of this equation by hypotenuse squared, then I'll end up with, using the properties of exponents to simplify that left-hand side, we have the opposite over hypotenuse squared. We have the adjacent over hypotenuse squared. And on the right-hand side, we have 1. Opposite over hypotenuse is sine. Adjacent over hypotenuse is cosine, giving us sine squared theta plus cosine squared theta is equal to 1. Notation on exponents of trigonometric functions is hideous, and I wish it wasn't done this way, but there is so much history behind it that I have no hopes of saving it, so it's important for me to teach you how most people notate these exponents. But we're putting the square on sine. What we really mean is take the sine of theta and square it, and take the cosine of theta and square it. But we write it as sine squared theta plus cosine squared theta because it's a little bit easier to write, and that's what everyone does, so it's important that you know that notation. That's the most common Pythagorean identity. It's certainly not the only one. I chose to divide both sides of the Pythagorean theorem equation by the hypotenuse. I could have just as easily decided to divide both sides by the adjacent or by the opposite. Had I divided by adjacent, I would have ended up with tangent squared theta plus 1 is equal to secant squared theta. And if I had divided by the opposite, I would have ended up with 1 plus cotangent squared theta is equal to cosecant squared. So there are 2 other forms of the Pythagorean identity. Our goal is to use these properties along with the natural properties of algebra right? Combining like terms, canceling a common factor between the numerator and denominator, and so on, as a way of showing that the expression on the left-hand side of an equation is the same thing as the expression on the right-hand side. And with that, we show that we have something that is an identity.